This lecture is on the posterior distribution of a Poisson model or a Poisson distribution. So before we start, we have to know what a Poisson distribution is. Just like a binomial distribution, a Poisson distribution is a discrete distribution. And it is typically used for count-type data. And if the random variable x has a Poisson distribution, then its possible values are 0, 1, 2, 3, all the way up to infinity. So let's take an example. But before we get to the example, the density of a Poisson random variable is probability x is equal to sum x lambda t raise x e raise negative lambda t divided by x factorial, where lambda is called the parameter and t is a measure of time. Time, it could be a measure of space, it could be area, it could be density, and so forth. So here is an example. Suppose the number of patients who arrive at an ER has a Poisson distribution with lambda equals 4 per day. Well, let's say 14 per day. And the question here is, what is the probability that the number of patients who arrive at the ER is A, exactly 18 per day, and B, exactly 32 per 2 days, at most 50 per week. So let's start with A. exactly 18 per day would simply imply that lambda is 18 and t is equal to 1. So what we have here is, lambda is 14, since we have 14 patients arriving at the ER per day. So, and the value of x is 18, and we want to find the probability that x is equal to 18. So we simply have to plug it in the formula, 14 times 1, that is lambda times t, raise x, e raise negative lambda times t, divided by x factorial. So it's a complicated formula. 18 factorial simply would mean we start at 18 and multiply all the way down to 1. Now, if we have the calculator, we can use the Poisson PDF function to find this answer. So this would simply be 18, 14, and that ends up being 0.0655. Now, if we have to use it and find this manually, it's 14 raise 18 times e raise negative 14 divided by (18 factorial). Seems to be slightly off. I wonder why. Strange. Let me quickly check this. Perhaps I'm using the wrong syntax here. It's backwards. So it is actually (14, 18). So that ends up being 0.0554. So if we have to use the calculator, Poisson PDF, the first value would be lambda t, and the second value would be x. So there is about a 5% chance. So now we want to find the probability that we have exactly 32 cars per 2 days So that would mean we have probability x is equal to so lambda would be 14, t would be 2, because we are looking at 2 days, and x in this case would be 32. So probability of x equals 32 would equal to 14 times 2 raised power of x, which is 32, e raised negative 14 times 2 divided by 32 factorial. So we can use the calculator to find this answer. So lambda t should go in first. Which is 28, and we follow it up by 32. And that probability is 0.0535. It sort of makes sense, because 32 is very close to 36, and 2 times 18 is 36. So we're pretty much finding the same probability as part A. And the last one, we have at most 50 per week. Now, we have about 14 cars per day, and times 7, we have about 98 patients that we expect. If we're expecting 98%, and the question here is, what are the chances that we only see at most 50 per week? It is likely to be small. So let's see if we can get to that answer. So lambda is 14, and t is 7, x is 50. But the key phrase here is at most. So since it is at most, we have to use probability of x less than or equal to 50. And that involves a complicated formula, so we're just going to rely on the calculator here. So we would press second vars, and select option D and enter 14 times 7, comma 50. And that is a very small value. Now, what if we change the problem and say, for example, probability x is at most 100. Let's see what probability we get. And that happens to be 60.58%. So this makes perfect sense. Again, the reason for that is we expect to have (14) patients per day, which would simply give us a guess. This would imply per week. The expected value is 14 times 7, which is 98. So give or take, we need to have 98, or we would expect 98 patients. That said, for us to say, well, what is the probability we would only see at most 50? That is going to be a slim chance. What is the probability that we would see at most 100? It is going to be quite high. So, in general, the expected value, in other words, the theoretical mean and variance of a Poisson random variable is simply lambda times t. So in our example, 14 per day, 14 times 7, expected value on average, we would expect to have 98 patients. So, so now suppose we collect observations from a Poisson random variable with rate lambda. And let's say the observations are x1, x2, x3, all the way up to xn. So we are trying to find the posterior distribution for lambda. So we know the probability of lambda, which is our parameter, so that would be our usual theta, given the data, which is the sample or evidence, is equal or proportional to the probability of the data given lambda, which is the likelihood multiplied by the prior. So the likelihood here, just like we did it for binomial, we have n observations, so x1 all the way up to xn given lambda is simply the product of I equals 1 to n probability x is equal to xi. In other words, we simply have the density lambda t raise xi e raise negative lambda t divided by xi factorial. Now, the denominator doesn't have anything to do with the parameter. It's independent of the parameter. So when we plug it in the likelihood, we could simply write it as probability lambda given the data is proportional to times the prior. So since that entire thing is in product, so we have a common base and we are multiplying it n times to itself, so the power there would be 1 to n xi times e raised minus n lambda t multiplied by the prior. So we know the concept of a conjugate prior. So the appropriate prior is a gamma distribution, and it has two parameters, alpha and beta. So what is a gamma distribution? So a gamma distribution for the prior would simply look like this. So that there is a parameter, lambda, and we have lambda raise alpha minus 1 e raise minus beta times lambda divided by beta raise alpha multiplied by gamma of alpha. So that is a gamma function, not the same as the gamma density. You don't have to know about this formula, but you can look it up if you want. So it has two parameters, alpha and beta. So beta is what we call the scale parameter, and alpha is the shape parameter, and gamma is a skewed distribution. And it is defined for positive values of lambda only, and we know that lambda is positive. The number of patients arriving at the ER, for example, is a positive quantity. So the likelihood is defined using that density, and the expected value with parameters alpha and beta is alpha times beta. It's alpha over beta. And the variance is alpha over beta squared. So the choices of alpha and beta would determine how the skew of the density would be like, and in turn it is going to affect the estimation of our parameter lambda. So key things to note: a gamma distribution has an expected value alpha beta, and variance is alpha over beta squared. And this is going to be the conjugate prior for our Poisson model, and you would see why soon. That beta raise alpha should be in the numerator. It's a mistake. Okay, so now going back to our expression here. So there is our prior, the last part. So the posterior of lambda given data is proportional to the likelihood, which is lambda t raise sum I equals 1 to n xi times e raised negative lambda t multiplied by the probability of lambda. So the t over there sort of presents itself as a problem because it is easier to have it in terms of t, but then here we end up having just lambda in the parameter. So the prior affects only the value of lambda. So regardless of that t, we could come up with an appropriate prior. So what do I mean by that? So instead of writing prior of lambda, I could write it as lambda t itself, and do a little bit of trick here. Call it lambda star to be equal to lambda t. So probability of lambda star given d is proportional to lambda star I equals 1 to n xi e raised negative lambda star and probability of lambda star. So now I could just use the formula that is over there and replace lambda star or lambda by lambda star. So we have lambda star raised alpha minus, e raised negative lambda star multiplied by lambda star raised alpha minus 1 and e raised minus beta times lambda star. So if t is equal to 1, then that would simply mean lambda star is equal to lambda. So per unit time, lambda star would simply be equal to lambda. In other words, per day, per month, if the rate is per unit measurement, then we could simply replace lambda star by lambda because it is simply lambda times 1, which is lambda. So probability of lambda star given d would be proportional to lambda star raised that term and that term are identical, so we add the powers and that power and that power have a common base, so we add the powers and I forgot the n over there. N. So we would end up getting this expression, lambda star raised that term and e raised lambda star times that term. If you closely observe, this expression has a form very similar to that expression right there. So lambda raised alpha minus 1, e raised beta times lambda. So this pretty much is a gamma distribution. Here alpha would be sum I equals 1 to n xi plus the prior value of alpha, and the new beta would be n plus beta. So our conclusion is the posterior distribution. So, which is the entire purpose of going for a conjugate prior, because if we have a conjugate prior, the posterior will look like the prior. So we nicely got this expression. So we can now find the posterior mean since we know that the posterior distribution is gamma. I wrote the expected value of gamma is alpha over beta. So we would have sum I equals 1 to n xi plus alpha over n plus beta. And the posterior variance is sum I equals 1 to n xi plus alpha divided by n plus beta squared. So we're simply dividing alpha post over beta post, alpha post over beta post, because the posterior distribution is a gamma distribution. So we all know that the sample mean x bar is the sum of all x values divided by n. So which would imply the sum of all x values would be equal to n times x bar. So I could rewrite mu post the posterior mean as nx bar plus alpha over n plus beta, and the posterior variance as nx bar plus alpha over n plus beta squared. So an important remark about the posterior mean. So I could rewrite the posterior mean as nx bar over n plus beta plus alpha over n plus beta. And if I pull n out from the denominator, I would have 1 plus beta over n plus alpha over n plus beta. Mind you, this second term is the contribution of the prior. So that would be prior information. And that right there is the sample mean. And the beta in the denominator is from the prior also. Now what would happen if n gets substantially large? So let me go ahead and cancel those two n's, I would have x bar over 1 plus beta over n plus alpha over n plus beta. So when n, i.e. that is the sample size, increases significantly, then the second term will go toward 0. So as n gets larger and larger, that term would go towards 0, and that term would go towards 0, and we would simply end up having x bar over 1 approximately, which is x bar. So if you recall earlier, when I started Poisson, we had the expectation as lambda t and the variance as lambda t. Right there. In other words, the mean gives us the value of the parameter. That's exactly what we are trying to say. If the sample size is significantly large, the prior has nothing to do with the value of the parameter. The prior does not affect the parameter. All you have to do is find the sample mean. However, if the sample size is small, then prior information could actually change how we interpret the posterior. So here is an example. So the number of patients per day over the past week, it's shown below, and this is what we have. And prior information indicates that the prior is gamma 5, 2. So we want to find the sample mean. What is the posterior distribution? And assuming normality, what is the probability that lambda is greater than 12 that is, the number of patients and we'll also find a 95% confidence interval or high density interval for lambda. That is our parameter. So let's start with the mean. Finding the mean is quite straightforward. So we have observed a week, so I need one more day, so let's go ahead and add another, let's say 10. So we have information from 7 days, and day 1 we had 16 patients, day 2 12, day 3 13, and so forth. But previous information tells us that the prior is gamma 5.2. So let me go ahead and enter the sample information. The mean ends up being 12.28. We could round it and have it as 12.29. Now we want to find the posterior distribution. We know that the posterior distribution for lambda, which is simply the number of patients visiting the ER per day, is also gamma, but its parameters are alpha post, which is sum xi plus alpha, and beta post is n plus beta. So alpha post, here we have the sum of the values, which would be n times the mean plus alpha. So 7 times 12.286 plus alpha, which is 5. So we would end up having the sum is 86. You could see it in the second line on the calculator screen. So 86 plus 5. So alpha post is 91. The posterior value of beta is simply the sample size, which is 7. 7 observations plus 2, we get 9. So the posterior distribution is gamma 91,9. So let's find the probability that lambda is bigger than 12. Now, the average seems to be 12.128 per day. So could it be bigger than 12? It is likely. Did the prior information change that value 12.28? It's likely we would see how the prior information affected the value of lambda. So going back to the posterior mean, that is simply alpha post over beta post. So we would have 91 over 9. 10.11. So important thing here, notice the sample mean is x bar equals 12.29 and the posterior mean is 10.11. So in this case, with Poisson, the mean and the value of lambda are one and the same. So we can clearly see that the sample mean was adjusted and it was brought down to 10.11 because of the prior information. So the variance for the posterior distribution is alpha posterior divided by beta posterior squared. So we have 91 over 9 squared. Which is 1.1234. Wow, interesting. It's 1.123456, but not 8, 7, and 9. Fascinating. Okay, so we want to use normality to determine if the probability, or what is the probability that lambda is going to be bigger than 12. So with only the sample information, it seemed like it is going to be about 12, but let's see how things change. So we will do normal CDF. We start at 12, E99, the posterior mean, which is 10.11, the posterior standard deviation, it's 1.058, which is simply the square root of 1.12. So there is only a 3.73% chance that the lambda is going to be bigger than 12. Again, if we thought about it from an intuitive perspective, the sample mean was 12.29, which is right over here. And the prior information is bringing it down furthermore to 10.11. So in the case of a Poisson, the posterior mean or the sample mean is the same as the rate parameter. So based on the average, we would expect about 12.29 patients without the prior information, or 10.11 patients with the prior information. And here in this question, we would want to find the probability that the number of patients would be greater than 12. It is going to be unlikely, because by all means, the prior drove the mean of 12.29 down to 10.11. So we next find a 95% confidence interval or high density interval. So first step is to find the margin of error, which is the critical value 1.96 multiplied by the standard deviation. So we have 1.96 times 1.058. That is 2.074. So lambda would lie between the estimate for the lambda, in other words, the posterior mean. The posterior mean for lambda was 10.11 minus 2.074, and 10.11 plus 2.074. So lambda would be between 8.036 and 12.174. So clearly we're saying that there is a (95% probability that lambda, which is the number of patients, who visit the ER per day, lies between 8.036 and 12.174. That said, well, what are the chances that it is going to be bigger than 12.174? It has to be less than 5%, and that confirms the answer that we had in the previous part. So that would be the posterior distribution with a conjugate prior of gamma in a Poisson model.